Ok, alors je démarre l'enregistrement. Super. Eh bien, écoute, on attend 5 minutes, c'est comme toujours.
Oui, d'accord. On voit l'écran. On voit la présentation.
Oui, on voit ta présentation, il n'y a aucun
Ok,
problème.
ok.
Il n'y a aucun
Très bien.
problème.
Très bien.
On va laisser les gens arriver et effectivement, il n'y a aucun souci, on voit bien ta présentation. On attend encore toujours 5 minutes avant le début, ne vous inquiétez pas. Martin est bien présent. On commencera vers 16h35, un truc comme ça. Alors, je vais présenter en quelques mots Martin, à qui je dois d'avoir fait connaissance avec GPT-3, puisque Martin m'a introduit, m'a présenté GPT-3 il y a quelques mois et je l'en remercie. Martin est suisse, nous vient de l'Université des sciences appliquées de Zurich et il est ingénieur et travaille sur les larges langages modèles, donc sur les outils qui sont rendus très célèbres en littérature et en art ces dernières années, et des outils qu'on connaît très superficiellement. Et c'est pour ça que je pense qu'il est particulièrement intéressant et particulièrement sensible d'avoir une interprétation, une analyse des enjeux contemporains de ces outils à partir d'une réflexion sur leur technique. Et c'est pour ça que je le remercie vraiment beaucoup de plonger au cœur de ces outils en nous expliquant comment ils fonctionnent et comment interpréter leurs résultats. Merci beaucoup, Martin. Je te donne la parole. Et sa présentation sera en anglais, hein, bien sûr.
Merci beaucoup, Alexandre, pour l'invitation. Je trouve ce séminaire très intéressant. Pour la présentation, je vais changer pour l'anglais. So, welcome everyone. My name is Martin Schuele. I'm from the Zurich University of Applied Sciences. I have a background in physics, but now I do mostly machine learning and deep learning in computational life sciences, and sometimes also with large language models, because also in life sciences there's a lot of text, and if there's a lot of text, these models are very useful. So I will talk about large language models. It will be rather technical, and in fact it takes quite a few slides to give an introduction. But at the very end, I would like to add some philosophical considerations, because I also have some training in philosophy. And I think it's interesting to think about how to interpret these models. Okay, as you probably know, the latest generation of large language models, such as GPT-3, got quite famous. Maybe you have experienced a bit with them too. So, for example, they can write quite accurate newspaper articles. They can conduct rather reasonable dialogues. They can write programming code. And this is one part of large language models, which is already actively used. And they can also be used for creative work, such as writing a play. And in fact, just like 2 or 3 months ago, there was a theater staged here in Zurich, Switzerland, where they used text written by GPT-3. So I believe this technology, whether we like it or not, will become an integral part of our lives. Now, what is the reaction of the public, or maybe academics? I would say it's rather mixed. So on one hand, we have this hype, AI hype, was a hype surrounding GPT-3 and other large language models. On the other hand, many people, especially philosophers, say, well, yes, these models are impressive, but they're just doing statistics, they're mere syntactic, they're just associative machines. And large language models do not really understand what they're doing. And I think that this is kind of a preliminary judgment. And I believe we really have to look closer at what large language models actually do and how we are going to interpret what they're doing and whether this is some sort of understanding or not. So I would like to give an introduction to large language models now. So as the name says, they're large deep learning models that model language. And there are different such models around, the best known being the BERT model series and also the GPT series models. And large refers to the number of parameters that are trained. So the GPT-3 model, for example, has 175 billion parameters, which is a lot, but there are even larger models, such as the 530 billion parameter Megatron Turing NLG model. So to give you an idea of what such large language models are capable of, I believe you may have experimented with such models yourself, but here are some additional examples. So for example, they can generate text So the task here given to GPT-3 is write the text on Leon Blum's legacy. And the machine goes on like Leon Blum was a French politician who served as Prime Minister of France 3 times, and so on. And Blum was a highly influential figure in French politics, and his legacy continues to this day. His advocacy for social reform and workers' rights helped to shape the French welfare state, and so on. So it's, I would say, quite a coherent text on Blum's legacy. And if you don't like it, that's also a nice thing with GPT-3. You can just hit the refresh button and you get a new text, which is slightly different to this text here. And another example is factual answering. So you give GPT-3 a question and then it should answer correctly. And the way how to do this is to give some examples. We will see why this is the case. So an example would be, how does a telescope work? Telescopes use lenses or mirrors to focus light to make objects appear closer. Or where were the Olympics held? And then the question I posed, how did Leon Blum die? And GPT-3 answered, Leon Blum died of a heart attack on August 30th, 1950. So GPT-3 is quite good at answering such questions and quite confident. And so I believe GPT-3 right away, but in fact the date is wrong. It's March and not August. So it's 1950, but March, not August, and the 30th, but not August, but March. So, you know, it can be the confidence that GPT-3 shows can be misleading sometimes. And then another example, text translation. So the task is to translate the following text into first French and second Japanese. So the text goes like, as a young man, he was most notably an expert on Stendhal, who was perhaps his strongest early influence. If Blum was, as he was called, the first true Stendhalian of modern times, and so on. And the French translation is quite accurate as far as I can judge. I don't know about the Japanese translation. And so I would say this is quite good. And you have to keep in mind that GPT-3 was not designed for translation tasks. So it's a general language model. And this is just one capability of GPT-3. Okay, so what are large language models? They are, as the name says, language models. And language models are mathematical models that model language with probability distributions. So we enter here kind of a technical part. So some text data S is modeled with a probability P of S. And S can be a sentence, a paragraph, or a document, depending on the application. Then, in order to work with text, we need to turn the text into numbers, or so-called tokens. So we turn, for example, the words of a text into tokens, and we then get a sequence of tokens. And the tokens basically indicate the word in some vocabulary. So we need a vocabulary, and we are enumerate the words and turn the words into numbers or tokens. Then the probability P of X says how likely some sequence X is. So for example, it would assign a probability to the sentence, the students opened their books. So language models are statistical models. So they model language with probability distributions, and it's not a deterministic machine. So that's also why, for example, with GPT-3, you can get different answers. You say, I mean, GPT writes a text, but it could also write some other text. It's a probabilistic or statistical thing. Now, the typical way to model these probability distributions, to model the token sequence, is to use the so-called chain rule, which builds up these joint probabilities by this expression here. So, for example, with the example sentence we had before, we would first have the probability of the, and then the probability of students given the, and then so on. So we build up these probability distribution, and this is called autoregressive sequence modeling, because at each time step, the future, so that the next token is predicted based on the past tokens, the past context. And that's also how GPT-3 works. Now, why are these language models important? They are important because many, if not most, NLP tasks somehow involve language models. So, for example, you can generate a dialogue by conditioning the text on previous dialogue fragments. Okay, so you always condition on text you have seen before or heard before, and based on that text, you generate like the next words. And by this, you can generate a dialogue. Or you could use it for language recognition, like similar sounding words such as speech and speech can be distinguished by recourse to a language model, which models the context of a word occurrence. So most NLP tasks are somehow related to a language model. And also, for example, GPT-3 is essentially just a language model. And as it can be demonstrated in numerous applications, it's nevertheless very versatile. Now, before the advent of deep learning models in natural language processing, such language models were developed or were modeled by statistical models, or so-called n-gram models, which determine the probability of words based on the relative frequency of a given word in the data set. So you would just count the occurrences of words, and based on these counts, compute probabilities. But these n-gram models become statistically and computationally inefficient with increasing context length. And this limits the richness of the language they can model. So nowadays, deep learning models, techniques have really replaced these statistical models and are now state of the art. So why are the novel large language models so good? I believe it's, well, due to different things, but mainly the following factors. So first, we have distributed representations of language, which is kind of a novel thing in coming from deep learning. We have then second, novel deep learning architectures. And third, we have very large models, which are also trained on very large data sets. So I would like to look at these things now in turn. So first, distributed representations of language. Well, in order to compute with language, we need to convert, for example, words into numbers, or so-called tokens. And the easiest way to do so is by enumerating a vocabulary and thereby assigning a number to each word. But such an approach has several disadvantages, both mathematical and computational wise. And for these reasons, a new paradigm has emerged in natural language processing, which has been proven very powerful, called distributed representations or embeddings. And having a distributed representation means that we encode tokens, not by like a single number, but rather by a continuous vector representation. So, for example, the word "the" we would assign such a vector to this word and some other vector or array of data to this word and so on. And these vectors can be quite long, like 100 to 300. They can have a length typically of 1 to 300 elements. And by such an encoding, we actually map human language, these words, into a vector space. And there are several advantages, but one of the advantages is that we can, for example, compute distance between words or the points of this space, which might then be interpreted as, for example, semantic distance. And the dimensions of the embedding space may also encode some information. So there's an example here. So we have this vector representation of these words, like wolf, dog, tiger, cat. And if you have a well-trained embedding, tiger and cat are close by. So the geometric distance corresponds to some semantic distance. And also wolf and dog are somehow clustered. And we may also interpret the dimensions, like this dimension here is like encodes the fact that here we have cat-like animals and here we have canine animals. And this dimension here would encode that here we have wild animals and here we have domestic animals. So we may interpret these embeddings like this, but of course, this is a simplified example here. We have only 2 dimensions. So usually we have a high dimensional space. And also it's not always possible to give like a nice interpretation. But this is the idea anyway. Then how can we generate such word embeddings? Well, we can train word embeddings on a specific NLP task as an integral part of a neural network. So it will be like one layer of a neural network. Or we can use so-called pre-trained word embeddings. And one of the most popular training algorithms for a pre-trained word embedding is called word-to-vec. So it's an algorithm which maps words that share a common context to nearby points in the embedding space. And we can run this algorithm on large data sets, and by this gain a pre-trained word embedding, which might then be used further in downstream tasks, for example, for text classification or some other NLP task. Here we see an example of such a word embedding trained by Word2Vec. So here we have a 200-dimensional space with 200 dimensions. There's a vocabulary of 10,000 words. And so some words is picked here, students. And based on this word embedding, you can then compute like similar words, which are like the nearest points in the embedding space. So the nearest word would be students, and then teachers, and then school, professors, and so on. And what we see here is a two-dimensional representation of this 200-dimensional space, in fact. So it's a 200-dimensional space, and what we here see is just like a 2D representation of that space. Okay, so that's the idea of a distributed representation. That's one important point, I believe, in these developments. Then we come to the second, which is novel deep learning architectures. And the dominant model at the moment is in NLP is the so-called transformer model. Here you see a sketch of the architecture from the original paper. And it's quite complicated, but there are a few, I mean, the main factors which are being used are listed here. So we need the concept of embeddings, which I've just introduced. Then the concept of feed-forward neural networks, positional encodings, and the attention and self-attention mechanism. So I already introduced the idea of an embedding. So just a brief comment on feed-forward neural networks. So this is the basic ingredient of any neural network deep learning model. So it's feed-forward neural networks use this artificial neuron model, which is loosely based on how a biological neuron works. So some input signals are being summed and weighted, and some activation function is being applied. So this it's a very simple model of the biological neuron, but if you stack them together, you get a powerful network, a powerful computing machine. And these feed-forward neural networks also figure in more complex neural networks and deep learning models, also in the transformer model. Then there's a kind of new technique compared to other neural network architectures with transformers, namely that unlike other deep learning models, transformers have no inherent structure that would take into account the order of elements in a sequence. But the order of the elements in a sequence when dealing with a language is very important. So to make use of that order, some information about the relative or absolute position of the tokens, this information has to be added additionally. And the explicit way to do so by enumerating the words in the sequence, like you see here. So this has various disadvantages. So again, we have some so-called positional encodings, which are like a vectorized representation of these positions. And these vectorized positional encodings can be added to the input embeddings. So we have some embedding, and we add these positional encodings. And by this transform model knows what is the position of the elements in a sequence. These positional encodings can also be either fixed, as in the first transformer model, or they can also be part of the learning process. Then there's another component which actually made these transformer models quite famous. It's the so-called attention mechanism. So it's loosely based on this idea that our attention is directed by non-volitional cues and volitional cues. So non-volitional cues would be something that you're immediately drawn to, like, you know, the car in this picture and this sign here. And this can actually can be modeled quite good with, for example, convolutional neural networks. But we also have something like volitional cues. So we can, you know, direct our attention specifically to some part, maybe, I don't know, the rocks in the background, which we are not our eye is not immediately drawn to this part of the picture. But if we want to do so, we can direct our attention to these parts. And the attention mechanism in these models, they are somehow designed to allow for this. It's a kind of special terminology is used in this context. So the sensory inputs would be called values. The non-volitional cues are called keys, and a volitional cue is a query. And what is shown here schematically is the idea that you compare key queries and keys by some mathematical function. And this is also called attention pooling. And based on this attention pooling, the values are actually selected. So it's a kind of a retrieval mechanism where you can design how to retrieve some elements or some values of some, for example, sensory input. And you can either design that certain elements are being retrieved, or you can, and that's how it works with, like in these deep learning models, you can learn which elements are to be extracted to in order to do some tasks in the best way possible. So mathematically, this is modeled by this expression here. And so what you see here is a so-called attention scoring function, which maps these key value pairs to a scalar. And we might have different choices of such attention scoring functions. The attention scoring function used by transformers is given by this expression here. So it's basically a dot product comparing keys to queries. Now in the transformer model, these attention mechanisms enter in two places. We have some self-attention mechanism here. So there are two parts, an encoder part here and a decoder part. We have some self-attention mechanism, and here we have some attention mechanism. So the original transformer model was designed for language translation tasks. And the idea is that the encoder encodes the source language, the decoder encodes the target language, and we have a self-attention mechanism, but we also have an attention mechanism which allows to compare like the two representations. So to give you an idea or an example, this attention mechanism allows to attend to parts of the input sequence that are deemed relevant to the current prediction. So, for example, if you face the problem of translating the sentence, the agreement on the European Economic Area was signed in August 1992 into French. It's the straightforward way to translate this is just to translate the sentence word by word. But as we know, this is a bad idea because in French love to flip things. So the European Economic Area turns into the Zone économique européenne. So these words are flipped, and we also need to pay attention that la zone is feminine, whereas the area, so we don't have this in English, but the model needs to see that, okay, area is translated to so, la zone, and that's a feminine word. And the transformer model is designed to address these issues. So what we see here is a plot of these attention scores, which indicates what the model pays attention to when translating this example sentence. And we see that we see here that, so here, that it notes that these words have to be reversed. And also, for example, the word la pays attention to the and area, indicated by these light colors here. So the model has learned to pick up these characteristics. Okay, so that's the attention mechanism, which allows to compare these two encodings, these two representations of language. But there's also a self-attention mechanism, which means that the queries, keys, and values come from the same data. And this mechanism then allows the input elements to interact with each other and find out what they should pay attention to. So for example, in the sentence, GPT-3 is better than GPT-2 because it is bigger. It allows for noting that it refers to GPT-3 and not to GPT-2. Okay, then the next important thing I want to mention is that, so the word embeddings we had before the advent of the new kind of models, such as the transformer model, they were able to generate a distributed representation, but the representation will not take context into account. So for example, the word play in the sentences, he will play on Sunday and he will play tricks on you, would have the same representation. So the word play is just encoded by this vector representation, but it would be the same representation for different contexts. Now with the transformer models, we get in contrast, we get a context-sensitive representation. And we would get for a different context, we would get a different representation of the word. Now, what distinguishes these models is the context size. So BERT has like a context, and these are large models. So, you know, people started with like a small context size, but now BERT has like 512 token context size, and GPT-3 has more than 2,000, a context size of more than 2,000 tokens, which is about, I don't know, 50 to 100 sentences. Okay, I would now like to talk briefly about the two, like I would say, the two main families of large language models. First, we have BERT. So that is a family of transformer models that represent tokens based on bidirectional context. So BERT would actually, when it generates a representation of a word, it would actually look at the context to the left of the word and to the right of the word. And it generates the representation based on two tasks. The first is masked language modeling. And the second one is next sentence prediction. So in the masked language modeling task, the task is to predict the mask tokens in a self-supervised fashion. So that means that we just, for training, we delete certain words from some text data set. And the task is to predict these deleted words. So that's the masked language modeling task. The next sentence prediction task is just the task to predict the next sentence. And BERT is trained on these two tasks. It can be trained on a very large data set. We get this context-sensitive representation, which can then be used for further or more specific natural language processing tasks, such as text summarization or text classification. So we need to fine-tune BERT then to some specific NLP task. And I would say that's the main, at the moment, that's the main approach in NLP. And there exist platforms where you can download BERT models and you fine-tune it to some specific problem. And this works quite well and you get nice results. And it's still feasible to do for, you know, people like me. Okay, then GPT-3, it's a similar model, but nevertheless, it's on one hand, it's similar. On the other hand, it's quite different. So GPT-3 is a very large language model with 175 billion parameters. And it has also been trained on a very large data set, about 55 terabytes of text data. And it's just a language model, an autoregressive language model. So it's the model I've talked before, just before. So it's really just a language model. It predicts the future tokens by looking at the past tokens. And it's not explicitly built for specific NLP tasks, such as to store facts or to do translations. It's really just a language model. Nevertheless, it's very good at it. So why is this possible at all? So with BERT and these other models, NLP tasks, they're usually approached with supervised learning on task-specific data sets. So, for example, if you want to classify the text, you fine-tune the model on this task. So you have supervised learning. You know, you have text data and some labels, and the model is trained on this data set. But GPT-3 demonstrates that this task can be learned without explicit supervision when you train it on very large data sets. And this is made possible. So this multitask learning is made possible because the model can be conditioned not only on the input context, but also on the tasks. So within this probabilistic framework of language models, learning to perform a single task can be expressed by this conditional distribution. So you have some input and you want to estimate the probability of some output. But with GPT-3, the model is not only conditioned on some input, but also on some task. And then GPT-3 can be applied without a parameter updating or fine-tuning. And the only interaction with the model is by the prompt, by text. This also means that GPT-3 can do few shots or one shot or so-called zero shot learning. So I show you some example here, which should make all of this a bit clearer. So in the approach before GPT-3 and these kinds of models, we had some, we had BERT, which generated some language representation, some embedding. And this would then be the input to some fine-tuning task. So if we face the task of, if you have a translation task, like sea otter to l'outre de mer, we would provide this data to the model, and the model would be trained on this kind of data. We give the input and the output. So these are the labels, and that's the supervised training going on. But with GPT-3, there's no supervised training. So rather the task is part of the input. So the task is translate English to French. And we give some examples here. So there's no further training involved, no supervised training. It's that the model is rather conditioned on these examples. And this is called few shot learning. Why is this possible? It's possible because GPT-3 was trained on a huge amount of data. And this data contains apparently enough examples of some input and some task. So for example, if it looks at data, high school exam data, often there it's written, translate these sentences to French, for example. So GPT-3 saw examples not only of like French to English, but also like a description of the task. And this can be carried on so that we actually have one-shot learning, where we only give one example, and even zero-shot learning, where we give no example at all, but we describe the task as text to the model, like translate English to French, and then choose, and GPT-3 has to deliver the answer. That's why with GPT-3 the prompting is quite important. Is really important. If you give more examples to GPT-3, it will deliver better results. So zero shot is much harder than like this few shot learning. So how you design the prompts, how you do the prompting is really decisive with models such as GPT-3. Okay, so how is GPT-3 then actually trained? Well, it's, as said, it's just a language model. So we have these conditional probabilities here. And we have some loss function which must be optimized. And this probability distribution is modeled by a transformer model. So the GPT-3 model is based on the previous GPT models. It's really a large transformer model with several like transformer layers. And then it's trained on a lot of data. Yeah, basically on the internet. So you know, some download of the internet, 400 billion tokens, some books, then the whole of Wikipedia. So it's really trained on a lot of data. It also uses a lot of computational resources. It's using 3,640 petaflops per second days. And only supercomputers achieve these numbers. So it's really needs a lot of computational resources. And that's also the reason why it was only trained once. So usually the deep learning models are being tuned, and you know, some hyperparameters are being tuned, and not with GPT-3. It was only trained once. Cost estimates, I read numbers from $5 to $20 million, but exact numbers are not available. So it's a really large model, and this is actually quite bad news for people like me, or like generally people at universities, which do not have these large budgets. Then what is also comes with these large language models is the observation that the capacity, the size is really decisive. And the performance is just better the bigger the data sets and the model size is. So this has also been studied, and what we can see is that if we increase the data size and the model size, the loss just keeps going down, and it follows some scaling laws, but it has not yet reached some bottom. So that's why people carry on with this, and even bigger models are being, you know, set up and planned. Okay, so that's the introduction to large language models. To summarize, large language models model language by generating a task-independent and context-sensitive and distributed representation of language. We might add a probabilistic. And by task independent, I mean the models such as GPT-3 are really, you know, it's a general model which can be used for different tasks. But of course, it was also trained on some specific, it was trained on a task, namely language modeling, but this nevertheless allows for a task independent representation. Okay, Now, do I still have time? Okay, so now I would just add some comments now about the interpretation of large language model. So what kind of language model do large language models possess? Well, in NLP, the only way to address this question is by analyzing, specific NLP tasks. So, and I don't see any other way how to do this. So language knowledge is like tested, is trained, tested, measured by some specific tasks. But the tasks can be very different, and you can have a wide range of, diverse tasks. So GPT-3, for example, was tested on like more than 100 NLP tasks, involving things like, language modeling, completion tasks. So for example, you would start with a story and GPT-3 would have to end the story. Then we would have question answering tasks. So typically like high school exams. Translation tasks where you have to combine grammar and semantics. Common sense reasoning tasks, reading comprehension tasks. Then we have superglue. That's a standard benchmark to test language models, where it's like a benchmark. It's a number of benchmark data sets where novel models are being tested on, which in itself involves a number of different language tasks. Then we have natural language inference tasks, tasks like doing arithmetic based on text, and some grammar tasks. So these models are really tested on a wide range of tasks. It's not just one specific task. It really covers, a wide aspect of like how we use language. Another interesting question is, okay, where does now this kind of knowledge, does it reside in these models? And there's like a meta study which looked at around like 150 papers that study these questions, and the answer is not conclusive. It's not really clear. But there are some observations which people more or less agree. So so this was about BERT, not about GPT-3. So it seems that the lower layers seem to encode things like word order. The middle layers of BERT seem to encode syntactic information, and the final layers are more task specific. What we can also say is that these large language models generate a hierarchical representation of language, and that semantics is really spread across the entire model. So you cannot really pinpoint, one layer, one neuron doing, which is in charge of some, I don't know, some specific association or anything like that. Now, do these large language models show some kind of understanding? Well, understand, that's a big word, and it opens like a vast philosophical discussion. So maybe this is an easier question. Do large language models understand the meaning of a word? And I would like to conclude with some considerations about this. And we can take recourse here to, philosophical theories of meaning. One of the most prominent in 20th century philosophy is the Frege-Russell theory of meaning. It's like a classical semantic theory. So briefly, in Frege's theory of meaning, he distinguishes the meaning of a word in a sense, so-called sense, and a reference of a word. The sense of a word is the mode of presentation, he says. It's objective or a common property of many. And in the same context, the same word should have the same sense. The reference, on the other hand, is the object itself, which we designate by its means. And there are words with a sense, but no reference. A standard example, which is also quite famous in the philosophical literature, is the morning star and evening star, which both designate the planet Venus. So they have the same reference. The planet Venus is the reference, but they have different senses. So the reference really somehow grounds the words in reality. And the sense is rather the representation of the word. A sentence can also have a sense and a reference. So a sentence, or rather a proposition, so Frege actually only talks about propositions, contains a thought, which is the sense of the proposition. The reference, on the other hand, is the truth value of the sentence. So by truth value, we mean the condition that the sentence is true or false. And Frege says we gain an understanding of a sentence when we grasp its thought, that is its sense, together with its reference, that is the truth value. Okay, now how can we judge whether someone grasps the meaning of a word? With the notion of sense, we are left only with a rather vague formulation that such as the sense is grasped by everybody who is sufficiently familiar with the language. But we might also say this because the sense and also the reference of a sentence results from the sense of its components. We may also say that we grasp the sense of a word if we grasp the sense of a sentence. So this is, with Frege, this is left rather vague. In regard to reference, this case seems clear. So I understand the reference of a word if I know the object that the word denotes. And ultimately, this comes with understanding the truth conditions of a sentence. If I understand a sentence to be true, I understand the references therein. Frege's example is anyone who seriously takes the sentence, Odysseus was set ashore at Ithaca while sound asleep, to be true or false, would ascribe to the name Odysseus a reference. So this classic semantic theory is tied up with the notion of truth, or a theory of truth. Now, how does this compare with large language models? Well, we may say that Frege's sense and the distributed representations used in large language models have some characteristics in common. So the same word may have different modes of presentation. And especially in the same context, the same word has the same sense. And they're also kind of objective representations. And his notion that a sense is grasped by everybody who is sufficiently familiar with the language, well, we may test this grasp with NLP tasks. I mean, yeah. How should we test whether someone is sufficiently familiar with the language? It's by conducting a series of language tests. Now, the concept of reference is obviously linked to the concept of truth. So if a sentence is recognized as true or false, its reference is also recognized. This means I would say that if GPT-3 can distinguish true and false sentences, GPT-3 also understands the meaning of these sentences, according to Frege's theory. And well, GPT-3 can correctly judge certain cases without problems, but in other cases, it has more problems. So it can give correct answers to, general questions, but when it becomes specific, GPT-3 is often wrong. So yes, GPT-3 can give factual answers, but in some areas, with some tasks, GPT-3 is having a hard time. Why is this the case? So obviously, GPT-3 has only learned from texts, and it lacks a grounding in reality, so to speak. I believe there are 3 possible answers to this criticism. First, we may say, okay, this analysis by taking recourse to Frege or this classic semantic theory, that's just fundamentally flawed. Another answer is the large language models of the future will be more grounded in reality. And the third answer would be, well, this is, the importance of truth theories in this context is really overestimated. I would just, because I'm over time, no, we're almost there.
No, Martin, there's no problem of time because what you're showing is so interesting. We are just fascinated, so take your time.
Okay, I've finished, I'm almost there. Okay, so obviously everything GPT-3 knows, it knows from text. It's like you being enclosed in your study and you're just reading books about foreign countries, but you never have set foot in any of these countries. And that's how GPT-3 gets its knowledge. But in fact, there is research on grounding these models with so-called multimodal models, which combine different data sources. So the typical example is combining text and vision. And so here you see one of these models, also by OpenAI, which generates like a combined representation of images and text. And by this, you somehow ground your language knowledge in some other data source, like for example, when a text speaks about dogs, the model can also associate an image with that language knowledge. And it has actually some amazing properties that it can actually classify pictures of things it has never seen before, just because it has read about these things in some text. But it was not trained on these kind of images. But by combining, the language knowledge with the thing that it sees, it can figure out what it sees, so to speak. So this is a very active research field at the moment, these multimodal models. Another answer is like more philosophical, like you could take recourse to a structuralist theory of meaning, going back to Peirce, the people like Umberto Eco expressed such theories. So according to Eco, he has written books about this, and it's like really a ridiculously small sample, just one slide, but I would just like to point out 2 things. So he says that the problem of truth and thus the problem of reference is post-semiotic. And meaning is rather a cultural entity. So language is a social phenomenon. Expressions that have no truth value can nevertheless be understood and have meaning. And the reference is replaced by something called interpretant, which is another sign, which is again determined by a further signifier and so on, leading to a never-ending series of interpretants, which is called infinite semiosis. So signs only refer to other signs, which again refer to other signs, and you never get outside of this, you know, this denotation mechanism. So words can only be interpreted by other words, which are again interpreted by other words. And you never really leave this universe. And that's what GPT-3 at the moment does. It lives in this universe of text data without an outside view. But according to Umberto Eco, this is also how we actually function. So the signified is a cultural entity that can be interpreted through a chain of interpretants that manifest themselves differently in different cultures. This process of signification takes place in a semantic field that is subject to a constantly changing environment, which is why these fields form a complex changing topology or structure. So, and this semantic field, it reminds me of, you know, these distributed representations that these models generate. And if I get Eco right, it's rather, the connection to reality is rather, you have this structure as a whole, which somehow maps to reality, but not a specific sign or a specific word, but it's rather this semantic field as a whole, which somehow has to match to reality. And I think that's also, when you compare it with GPT-3, I think that's why GPT-3 often gets correct answers without having like really a connection between the words it has learned and some outside reality. And then to conclude, there are also like pragmatic theories of meanings, like with the late Wittgenstein. There is a, like in the Philosophische Untersuchung, for example, he says that the meaning of a word derives from its use. The meanings of words are not defined by the objects they designate, nor by the mental images one might associate with them, but how they are used. So for a large class of cases, though not all for which we use the word meaning, may be defined. Thus, the meaning of a word is its use in language. And yeah, I mean, that's exactly what these large language models do. They derive, so to speak, a meaning, if we can speak of a meaning, by looking at how the word is being used in language tasks. So Wittgenstein introduced the notion of a language game, or also called the whole of language and of activities with which it is interwoven, the language game. And the late Wittgenstein believes that the questions, what is length, what is meaning, what is the number one, etc., causes us only mental spasms. And we are dealing with one of the great sources of philosophical confusion, and now makes us look for a thing that corresponds to it. So by this, I would like to conclude. I hope you didn't get mental spasms. And the research in NLP certainly continues, and these language games are being carried on. But I think it's also worthwhile to take a step back, as you people do in the seminar, and like think about, okay, how are we going to interpret these developments, which will happen anyway. Okay, thanks a lot for your attention.
Merci infiniment, Martin. Je crois qu'on peut t'applaudir. Je crois que tu comprends le français et donc je propose de faire quelques commentaires en français. Ça te convient?
yes.
You prefer in English, so.
Non. Oui, on peut discuter en français, mais peut-être je vais répondre en anglais.
D'accord. So, j'ai souvent pensé, comme toi, à Wittgenstein, avec la linguistique distributionnelle, la sémantique distributionnelle. Effectivement, c'est très, très frappant ce que tu as montré. Merci beaucoup de nous avoir rappelé un peu les modèles sur lesquels les larges langages modèles fonctionnaient. Cette question de l'apprentissage par transfert qui s'est démontré extrêmement performant, puisque maintenant on a utilisé des modèles d'apprentissage par transfert pour la connaissance d'images. Donc, ce sont vraiment des messages des modèles particulièrement intéressants. Merci de nous avoir montré la progression des modèles vectoriels jusqu'à GPT-3 en passant par BERT. Et j'ai posté un petit article sur le futur GPT-4 qui dépassera encore les 75 millions de tokens. Merci vraiment beaucoup de permettre de comprendre de l'intérieur ces modèles et au fond comment ils comprennent. En fait, tu nous as permis de comprendre comment ils comprennent. Et je crois que c'est vraiment très, très utile parce que en fait, on rencontre ces modèles en NLP, on les rencontre également pour tout ce qui est utilisation littéraire, culturelle et artistique de l'intelligence artificielle. Donc, ce sont des modèles qui sont absolument présents à la fois quand il s'agit de parler de l'intelligence artificielle pour la traduction, que de l'intelligence artificielle pour l'analyse en numérique et numérique des textes, que de l'intelligence artificielle pour ce qui est de la création. Parce qu'effectivement, c'est quelque chose que tu n'as pas tellement abordé, mais les LLM sont capables d'inventer des histoires à partir des histoires qu'elles ont apprises, même si ce sont des histoires qui sont toujours un petit peu courtes, ce qui est toujours un peu le souci. C'est une question justement que je voudrais te poser. Est-ce que il n'y a pas, de ce point de vue-là, des limites aux explications que peut fournir GPT-3 quand tu lui demandes quelque chose? Est-ce qu'il est capable de créer de longs textes et pourquoi GPT-3 n'est pas capable de créer des longs textes? Ce sera ma première question et ensuite on viendra peut-être sur les aspects philosophiques de ta réflexion.
Well, GPT-3 is limited by the context size. So it can look at maybe 50 to 100 sentences, and it generates, text based on this context. You can, I guess, you can produce longer texts, but they're not as good as these shorter texts because it's limited by the context size. So it has a limitation what it can look at.
C'est-à-dire qu'en fait, la taille du contexte d'apprentissage est la même que la taille des textes que de la longueur maximum des textes, c'est ça?
So it gives an answer based on the context. That's why these models are so good, because they can consider the context. And
but I was thinking on the size of the text that GPT-3 is able to produce, the stories, the explanation, the dissertations, the essays that GPT-3 is creating are somewhat limited in size. And I was wondering, why is it so limited? Why is GPT-3 not able to continue a story? Because yes, that's your slide on the one shot, few shots. Could you elaborate a little bit about this question?
Yes, so it looks at some context, but the size of this context is limited. So it can look at like 50 to 100 sentences, and it generates a text based on this context. So if you want, it's like you're reading a two-page paper, but you have to write the book based on this two-page paper.
Okay.
It's possible, but doesn't make much sense, right?
Mm, mm.
So there's the context, the GPT-3 is limited by the context size, which means the number of sentences it can look at in order to formulate an answer or to generate the text.
So it has no long memory. So it's a short memory.
Well, it's more than 2,000 tokens, so it's quite big. It's about 50 to 100 sentences, which is quite big, but it does not look at like the whole book, so to speak.
Mm.
But you can generate the text, and then you can play this iterative game. So the text becomes the new input, the generated text becomes the input, and then you generate more text, and the second text will be the new input for the next text. You can use it iteratively, right? And by this, you can also, construct a story, longer stories, by using it in an iterative way.
Okay.
But it doesn't make much sense to produce one long text in one go, because the model is limited by the context size.
Okay. Okay. Thank you so much. Est-ce qu'il y a d'autres questions? Je sais que Pierre Depaz travaille et s'interroge aussi beaucoup sur les langages modèles, n'est-ce pas?
Oui, bonjour. I did have a quick question about what is considered context or not, and when you make the difference between learning from the task and learning from the context, isn't the task considered context as well? Or is it very clearly different things?
No, it's with GPT-3, it's the task is part of the context. And that's really what it distinguishes it from the BERT models, where you like train the model on a specific task. But with GPT-3, the task is part of the input text. And this comes from this general, in AI research, one of the big goals is like this general artificial intelligence. And one aspect of general artificial intelligence is that you can tell that the system, the model, what it should do. It's like when you talk with a child, you say, okay, look, this is the sentence in English, and you need to translate the sentence to French. And the idea is that in the future, we will be able to communicate with these machines, like with a child, explaining the task, and the machine has not to be trained on the task with like a labeled data set with a lot of a labeled data set.
Mm-hmm. With a bigger and bigger context, I imagine then.
With bigger and bigger context.
What you were mentioning at the end, including different kinds of inputs, is it not a way to broadening the context?
Context, the limit of the context size is due to the model we use, the transformer model, which somehow limits that. But so what I also wanted to mention is that there's similar research now in vision, and the idea there is that you show the system, you show like you show the system some task, like throwing a ball, and the system is not explicitly trained on throwing a ball. It just watches, it's like children watching other children, how they do things, and then they do it themselves. It's the same idea here, that you give some inputs, but you also explain the task, and this is like one large input then to the model. There's no separation between task and the input. There's no separation between the English sentence, which has to be translated, and the description of the task. It's just one big chunk of text. Did I answer? I don't know
yes.
if I answered.
Yeah, that makes it clear. Thank you.
Any other question? I've got another one about the way you can train GPT-3 on additional corpus to create some customized GPT-3 because it's a service offered by OpenAI. You have to pay, but you can train GPT-3 or I don't know on some corporate text. How is it done? Is it easy to, can we ourselves download the model and train it ourselves on some?
No, it's not possible. It's not possible to download the model. So first, when you fine tune it, then you're doing it just like with the bird models. So you can somehow download the model, so to speak, and fine tune it on some task, but it's not like the main idea with GPT-3, because GPT-3 is really about like this zero-shot and one-shot learning. So that's the the research interest. So that's one thing. The other thing is you cannot download GPT-3 because it's too big. So you would have to use the API where you just constantly access through the API GPT-3, and you have to set up your system or whatever you want to do such that it constantly communicates through the OpenAI API. And it's not possible to download the model first because it has not been released, and second, it's too big.
Last question before leaving.
No, I have one. Sorry, I have one last question.
Pierre.
Regarding the question of meaning and whether those models understand what they're talking or reading about, do you think that there's going to be a point in the research where it needs to be clarified how the role of meaning in the creation of outputs, or is it possible to continue proceeding experimentally and keep on having experimental positive results?
Interesting question. I mean, AI research will continue. People will just continue with these models. I think it's philosophically, it's a theoretically interesting question, how to interpret these models. It's also a philosophically interesting question, I think. But I believe that in the future, it will also become a more pressing question, because once these models are deployed in our lives, so to speak, in daily usage, you will help them somehow accountable. I think that we will have a similar discussion as with autonomous driving. Who's liable for the autonomous car making an accident? And I think these models, they're only dealing with text, but nevertheless, they can have, I don't know, you can imagine cases where it has like real liability issues. And then somehow you need to get a clear picture of like what was the intention, or what these models think when what they have. I mean, you need some kind of interpretation what is going on when you have to, you know, judge certain liability cases, I would say.
Thank you. Yeah.
I mean, for example, such NLP models are already used to read legal texts or to, yeah, I mean, you know, these legal texts, they're often repetitive and it's kind of boring to go like this, like a 200-page treaty, and you can use these models, but the models might make a mistake, and then you would like to know why it made certain mistakes, or what did it actually think when, you know, doing what it does. So it's not just a philosophical question in the end, I mean.
Yeah. Thank you.
Merci beaucoup. Effectivement, on finit avec le retour avec le test de Turing et le test de la Chinese Book de Russell. Merci beaucoup à toi, Martin. Merci. Et je crois qu'on mettra en ligne ce qui sera vraiment une communication de référence. Je vous donne rendez-vous vendredi pour le Quick Work Meeting pour poursuivre cette discussion. Merci encore et bonne soirée. Au revoir.